Okay, so let's start. So I want to start by quickly finishing what we talked about at the end of last time. I actually decided to spend a little bit less time on it than I originally thought, because first we'll have a chance to look at these things a little bit more when you have a better understanding of what is why learning works, and it's related to this. And two, because frankly, this part is a little bit technical and somewhat boring, not really directly related to machine learning. So, but we do need to know this because it's important for us to understand what we're doing. So what have we done? We talked a little bit about metrics. We talked about accuracy, which you knew about. And I basically spent a little bit of time saying that accuracy is not everything. Sometimes you want to measure your performance otherwise. So we talked about recall, precision, and F measure. You will see this, in fact, in other problem sets. And the key question that I want to very quickly address here is that of comparing classifiers. So you have two classifiers, and you want to know which is the best, the one that you want to use later on in future predictions. So we agree that just looking at the training accuracy to choose between them is a bad idea. And in fact, even just looking at the accuracy or any other metric, I mean, I'm going to keep saying accuracy, but it could be other metrics, is also a bad idea. And the reason is that this single number may not give you what you want. So there's more to say about it, but very quickly I'm going to just address what you need to know in order to do homework one. So essentially, what we're saying, instead of a single test training split, train on this, test on this, give me one number, which is your accuracy, we're going to do n-fold cross-validation. You can think about n as ranging from 1, which means you just have a train testing, up to the size of your data. Right? So in principle, you can say, if I have m points, I'm training on m minus 1 points, testing on 1, on the remaining one, and I can do this m times, and then average. This is something that is called in the literature leave one out. We're not going to do this. We're just going to do 5-fold cross-validation, which is what I show here, which is considered a relatively robust statistic. So once we do this, we train and test n different classifiers, 5 in our case, and look at the average accuracy and the standard deviation of this accuracy. So basically, this is what we're doing. And now if we have two classifiers, you can look at the difference on each one of the 5 folds between them. And you want to ask yourself, is this good enough? Is this significant for me to say that classifier A is better than classifier B? Yes or no? And again, there are multiple ways of doing it. And I will come back to it a little bit later. For example, some of the things that will determine which test I'm using is, what else do I know about the classifiers? What data do I have about their output? Do I just have their performance, or do I have their predictions on all the data, and so on? But as I said, I'm addressing it in a very specific way, similar to what we ask you to do in the homework. And the key idea, or the key theory underlying what you're going to do, is something that is called hypothesis testing. So we want to know whether a specific hypothesis is true based on the data. The hypothesis could be something like classifiers A and B are different, or classifiers A and B are the same. So we define a null hypothesis. It's called A subscript 0 here, which typically will be the contrary of what we want to show. And we take some statistics, and H0 defines a distribution over these statistics. For example, this could be statistics over the difference in accuracy between algorithm A and B. And then we want to ask, can we reject this hypothesis? So again, the statistics, M, is going to be, say, the difference in the accuracy. I'm going to choose some significant value. I want to make sure that this happens with confidence 1 minus 0.1, 1 minus 0.05. And I'm going to reject the null hypothesis only if the probability of these statistics is less than this significance value. I think we ask you to look at it with significance 0.05. So now I have to compute these statistics, compute this probability distribution, and make this decision. So the null hypothesis, in our case, could be there is no difference between algorithms A and B. So the expected accuracy are going to be the same, modulo some difference, or the expected difference between them is 0. Now, of course, we don't know the distribution of these statistics, and we're going to estimate it empirically using this n-fold cross-validation. This is going to give us an estimate of this. So mu is going to be this difference here. We assume that it's 0. We're going to estimate it by looking at this n-fold. We're going to estimate its variance. And this test that I'm alluding to here is called Parity Test. It's paired because we are using, for A and B, exactly the same test data. So you can use this test only when this is valid. Sometimes when you want to compare your results to the literature, you may not be able to do this because you're not sure that you're using exactly the same data. And we assume that the distribution is a T, what is called the student T distribution. I'm not going to attend to why this makes sense, but we assume that this is the right distribution to look at, and therefore we accept the null hypothesis at significant level A if the statistics is within a small range that depend on A and depend on n, which is the number of folds, in our case 5. So once you compute this, you basically go to a curve of the T distribution, and you read off from there what is the significant level of the difference. That's basically it. So, and again, the idea is that we want to be able to get a little bit more confidence in the fact that, you have two algorithms. Every time you're going to run them, you're going to get somewhat different results. So how do you know? And in fact, it could even be that on some runs, A beats B, on some runs, B beats A. How do you tell the difference between them? So we want to get somewhat more robust statistics over this, and this is one recipe to do this. There's going to be more, so we're going to mention a few more as we go. Questions? Okay, so let's summarize what we said in the last week or so. We focused on decision trees. Through decision trees, which is an important and interesting learning algorithm and interesting hypothesis space, we also addressed a few other issues, mostly issues of overfitting, and a few other algorithmic issues like dealing with missing values and so on. We discussed the issues of expressivity of hypothesis space through this also. Hopefully, some of these points will become even clearer when you play with the data and your learning algorithms in homework 1. Okay, so let me shift gears here you can still think about questions that you may want to ask and move to what I want to be the next topic. Before that, a few administrative things. Okay, no problems with the registrations anymore. People can still petition if they want to switch 419, 519. What I'm going to say next is going to apply to it, or join the class, but basically we are done. Homework 1 is due next week. Homework 2 will be out next week. I'm really hoping that you started working on it. I know that many of you have. I want to remind you, and this apply only to a small extent to homework 1, will apply a little bit more to future homeworks. It's an applied machine learning class. I don't try to give homeworks that basically you give me back what we talked about in class, but rather you have to do some work, you have to think about what you're doing and what you see and why you see this. So the idea is, in the homework, is to challenge you on multiple dimensions so that you'll be in a situation that potentially is similar to what you'll be at next year when someone gives you a problem and you need to address it. So all the problem sets, we'll try to make them thus. Let's see what we can do. Okay, questions. Homework-related questions. Okay, too easy, I guess. Okay, so it's time to talk about projects. This is really relevant to 519 students. Even though, as I said at the beginning, if you are a 419 student and you really want to do a project, form a team, and you will not lose from doing a project. This comes with one caveat. I want to warn 519 students about teaming up with 419 students, not because they are not good people, but because with high probability, or at least non-negligible probability, toward the end of the semester, they become too busy, and since they don't have to do a project, they will drop from your team. So think carefully about this. 519 students cannot drop from the team because their grade depends on it. 419 can. So it has happened before. Even if it happens to one team, it's one too many. So think about it. How does it work? So I want to get proposals from you. So you should start thinking about it today if you haven't started already. The proposals are going to be short. 1 page, ideally, definitely no more than 2 pages. We're not going to look beyond that. We are going to give you comments or requests for change as soon as we can. I'm thinking a little bit about a mechanism for peer comments so that you can see other proposals. We'll see if we go ahead with this or not. But definitely start thinking about your project. Start teaming with people. So what is the project about? The project has to be a significant, or has to have a significant machine learning component in it. So many of you come or deal with multiple applications within computer science, outside of computer science. It's definitely okay that the project is about the applications you care about, but it has to be a machine learning project. Doesn't matter whether it's experimental, theoretical, even a survey paper, if you take it seriously, could be okay, but it has to be a machine learning project. As I say here, originality is not mandatory, but encouraged. I mean, really, I'd like you to make it interesting for us, interesting for you. So let me give you a few examples. So KDD cup, I'm giving here an example from about 5 years ago because it's an interesting topic still. author paper identification. Given an author and a small set of papers, we are asked to identify which papers are really written by this author. Data is out there. Author profiling. Given a set of documents, profile the authors. You can profile an author on multiple dimensions. Gender, identify the name of the author, native language of the author, many other things. Again, data for this exists, non-trivial project. File my emails better than Apple does. I talked about it at the beginning as an example. For some reason, they don't know what they're doing. Hopefully, you can do this better. There are data sets for that too. Caption control, look at YouTube. People write captions with high probability, or at least non-negligible, the caption is spam. Could be gibberish, could be just low quality text, could be unrelated completely to the image. Again, a machine learning problem. Adapt NLP program to new domains. So you're going to see this in your next problem set. Adaptation is a key problem in machine learning. We train a classifier on domain one, say on images that come from a specific domain, clean images, very nice images. You go to another domain, it doesn't work. You train a model on text, say news text, you go to email, doesn't work. And it doesn't matter what is the problem. So the issue of adaptation is very interesting, could be an interesting application. Work on making learn hypotheses more comprehensible. As we start today, we move away from decision trees, we're moving to linear classifiers, and later on neural networks. It's not clear why the classifier is making the decision it makes. It's hard to read off the classifier an explanation. This could be a very interesting project. There's been some work on it, really unsatisfactory. Develop a people identifier. So people step into my office, the door is closed, I want to know ahead of time who's there. So you can think about multi-sensory input, video cameras, audio cameras, I don't know, a carpet that takes other measurements of you and tell me who you are. Identify contradictions in news stories. Again, very interesting, very difficult, very timely problem. And there are many, many variations of this problem. Clustering. We're going to talk a little bit about clustering toward the end of the class, but if you're interested in these issues, many, many interesting problems in clustering. For example, large-scale clustering of documents, still not a completely solved problem. Naming the clusters, relatively open. So basically, there's a lot of stuff. One thing I wanted to point out, so I'm giving here an example of a Kaggle task. Some of you may know about Kaggle. There's a lot of data sets there. But just going to Kaggle to take a data set and run a few algorithms on it and comparing between them isn't a project. It's a project, it's not a good project. I mean, you really need to think a little bit more about what you're doing. So specifically in a project, I want you to have a thesis. You can use the Kaggle data set, but you still have to have a thesis. That's the point I want to make. Example, so last semester, people have done a really nice project. They had data, CT scans or MRIs, I'm not sure exactly where, for identifying and classifying internal organisms. So 11 different organisms, you take scans, images basically, and you want to classify them. Just the classification problem is uninteresting. You take data, you take a classifier, you run, you look at the numbers. Instead, we discussed it and suggested that they'll study generalization across various populations. For example, let's assume you learn only from male. Can you generalize to female? Can you do this across other populations, say age? And it turns out that actually they could say interesting things about the data when they split it various ways and try to study generalization. So again, the issue is not just to take a data set and run classifiers on it. I know you can do it. You will be able to do it definitely by the end of a few other homework sets. But really, I want you to think about it as a project. You ask a question, you have a thesis, and you're trying to address it. Questions? Yeah?
Where do you recommend we acquire these data sets? Online, or do you suggest collecting our own data sets?
In most cases, it's probably going to be easier for you to try to find data sets online. If you have specific polls that you care about and you cannot find, you can ask me. In extreme cases only, I would suggest creating a data set because it's a time-consuming problem, could be expensive. Unless you really need a new data set or you need to massage an existing data set, I would recommend don't spend your time on the data. Other questions? Okay, definitely start thinking about it. As I said, you have about 3 weeks or a little bit more to write a proposal. The proposal already has to indicate that you've thought about it, you know what you're doing. I mean, don't solve the problem by the time of the proposal, but at least show us that you've read a couple of papers about it, that you have good plans, and basically that you're on the right track. Okay. No more questions? Okay, so let's move on then. So where are we? So we talked about a couple of learning algorithms already. You've been playing with them. We talked about the importance of the representation as part of talking about it. And what I want to start talking a little bit about today is really twofold. One is to try thinking about how are we doing. So in the 80s, machine learning was an area where people developed algorithms. They had data sets, small data sets, and they would run the algorithm and look at the results and say, oh, this is a good algorithm, or this is a bad algorithm. So really there was no understanding of, can we say something about it beyond just running it on specific data sets? In the late 80s until early 2010, let's say, people have developed a lot of understanding of why machine learning works, when machine learning works. And this also, as we will see, helped us develop better algorithms. Because with understanding comes the development of better tools. People forgot a little bit about this now, and we are back to the 80s in some circles. But what I want to emphasize is that we can understand quantification. So we're going to start with this and do this mostly in the context of a new set of algorithms. All our linear learning algorithms. We're going to start with versions of Perceptron. You'll see that Perceptron is a very old algorithm. Was actually well understood in the 50s, many years ago. But basically what we are doing in machine learning today are variations of perceptrons with a few bells and whistles that the theory helped us understand that we have to add. So we're going to start with this, with a few versions of it, move to other linear learning algorithm like SVM, and then move to multi-layer perceptron. Okay, so today I want to really take a slightly more general perspective and think about learning protocols as a first step toward understanding this linear learning algorithm. So what does it mean, quantifying performance? So far, we don't know, for example, how many examples do we need to see so that we believe the output of the learning algorithm. So this would be one way to quantify performance. So, and this will be the first question that I'm going to ask. So here is a very simple function. This is the hidden function. So I'm thinking about the class of all conjunctions, monotone conjunctions. Dimensionality is 100. But really, the hidden function only uses 5 of them, x2, x3, x4, x5, x100. You don't know this, but you want to learn it. Remember that this is, in fact, a linear function. So this is a sample from the space of all linear functions, but it's easier for us. It's going to be easier for us to take this concrete, simple example and think about it. And the question is, how many examples are needed in order to learn it? And of course, how? Anyone wants to take a stab at that? So the reason no one says anything, I'm sure all of you are thinking hard, is because the problem is ill-defined, really. I really need to tell you a little bit more about the learning protocol. And in fact, there could be many learning protocols. Protocol 1, the learner proposes instances as queries to a teacher that knows the hidden function and can give labels. This is one learning protocol, right? So there is a hidden function, you are the learner, and you're going to ask questions, basically. And after a few questions answered by the teacher, you will know what is the hidden function. Question 2, the teacher takes the initiatives and tells you, I want to teach you this function. I'm going to choose a few good examples, show them to you. You learn the function from these examples. It's a different protocol, right? In the first one, you have no idea what the function is, and you have to choose examples. In the second one, the teacher that knows the function chooses the example in such a way that you will learn as fast as possible. And the third one is the protocol that has been popularized by machine learning in the last few years, and this is, there is some random source, nature, that generates examples. You don't know a lot about it, but there is some distribution that governs this generation of examples, and then someone labeled them, and that's the input to your learning algorithm. So, granted, protocol 3 is the one that has been studied the most in the machine learning area, and we're going to spend most of our time in this class talking about protocol 3. This is the one we talked about when we talked about decision trees. This is the one that you are basically dealing with in homework 1. It's not necessarily the most important learning protocol. The fact that it has been studied the most by machine learners doesn't mean it's the most important. Because most of the stuff that you've learned in your life, potentially outside perception, you have not learned from a random source of examples that someone labeled. You've learned more interactively. You've learned by asking, by reading, by being provided information one way or another. And I think that the way machine learning is going, if you guys are going to do machine learning in 5 years in some company or any other place, you will probably spend a lot of your time, and this is beginning to be the issue in machine learning, how do I get the data? How do I get the supervision for the data? This is what people in major companies today are thinking about already, because quite often this protocol 3 isn't sufficient. It's hard to label a lot of data. Anyhow, this is just motivation. And these are the 3 protocols that I want to study. So protocol 1, learner propose instances as queries to the teacher. Remember, there is a conjunction. You know that it's a conjunction, I told you, but you don't know which is the conjunction. What would you do? You are the learner. I'm looking for suggestions. Yeah.
Ask for the ones that are important, X1, X2, and X100. What are the questions you ask?
Yeah, yes. So what does it mean, ask for?
So it was a conjunction, right? So
Yeah.
we received all of them, right? So we just ask the important questions about that.
Okay, but give me, you're right, but give me a concrete question. So the way you're going to pose the questions is going to be as examples. So you'll give me an example, I'm going to label it for you. So what will be the first example you will give me?
I guess I would go like the opposite or say, imagine like, I don't know what the instant is, but like imagine if this is not true, this is not true, what is the outcome? Or I say like, I guess it depends on what exactly the questions are.
No, but I think you have the right idea, which is you want to know which of the xi's, you know there are 100 xi's, you want to know which one of them is in the conjunction.
Oh, you don't know which one is it? I thought you know.
Otherwise, there's no learning problem, right, if you know. Right, so remember, so what I told you is there is a conjunction over 100 variables.
So you don't know that.
You don't know, otherwise there's no learning problem. I just put it there so that we'll evaluate ourselves relative to what you propose. Yes?
I have a question about the question. What's the difference between protocol 1 and protocol 2? Because it seems like both, like the learner does not know about the function and not know about the key instances, like the
Okay. Good question. So what's the difference between protocol 1 and protocol 3? Suggestions? Yes.
Well, in protocol 3, the examples are given to you, and protocol 1, the learner generates the examples and asks.
Right. So in protocol 3, you don't have any control on what are the examples. There's some random source that generated examples, and the teacher labels them. In protocol 1, you, as the learner, can choose the examples. It seems more powerful, at least intuitively. Let's see if it is more powerful. Yes?
So I think I would go, if there's 100 features, I would go one by one. So let's say the outcome assumes, or like yes or no, depends on if it's a classification. I go from 1 to a certain amount, and whenever the answer changes to yes, I'll record like what happened, like which feature caused it to go the other way, and then I start.
Okay, good idea. Concrete example I want. Yes?
So you like set it up in like DNF or DNF and then like keep changing it?
Okay, but it's a conjunction. It's even simpler than CNF and DNF. It's just a conjunction. I told you that. So for example, if I give you the example, if you choose the example, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, up to 100, I'll tell you something, positive or negative. Let's assume I tell you negative. What have you learned? Yes?
When you're learning that specific example, you haven't really, I guess, been able to generalize it so much.
If I told you yes for it, what have you learned? Positive example.
That given input will generate the yes.
More than that, I think you learned. Let's think about it. Yes?
You learn that none of the ones that are false are necessary to make it positive.
Right. Yes?
I think what we can do is start by giving examples where only one of them is negative and all the rest are positive, and we just do that for each feature. And that way, every time we get a positive label, we know that the one feature that was negative is not a part of the conjunction.
Right. Yeah, excellent. So this is the simplest way I think, to think about it. So let's assume I give you an example that is all ones, right? You actually know what? You know that it's positive, right? Because I told you it's a conjunction. It's a monotone conjunction. So the true ones are going to be a subset of this. But now let's assume you drop x1 from it. If x1 is in the conjunction, I'm going to say no, right? That's basically your suggestion, right? If you don't give me x1 as on, x1 is off in my example, and x1 is in the conjunction, I'm going to say it's a negative example. That's because it's a conjunction. So here is what you're saying. The first example here, which is all ones except for one, the last one, 0, basically it's equivalent to asking, is x 100 in the conjunction? If I tell you that the value of the function is 0, the conclusion is yes, it must be there. You see that? It must be in the conjunction because when I turned it off, the value of the function is off. So conjunction means each one of the variables in the conjunction must be on for this to be a positive example. Right? So this way you can ask about each one of the bits. You can ask about, is x99 there, by putting all of them as on, except for x99, that will be 0. I told you that it's a positive example, which means you don't need x99 in your function. And so on. So how many questions will I ask before I get to the hidden function? 100, right? So I have to ask 100 questions, and after 100 questions, I get exactly the conjunction. Okay? I don't know if 100 is a lot or not, but that's what we have. So the dimensionality that we have is 100, and we see that this protocol forces us to ask 100 questions. And we got it, right? So when we ask about x1, the answer was no, we don't need it. When we asked about x100, the answer was yes, we need it. And so on about 2, 3, 4, and 5. Okay, so is it clear? As a puzzle, you can think about what would have happened if I did not tell you ahead of time that my hypothesis space is that of monotone conjunctions. For example, I would tell you it's general conjunctions. You can use negations. The function could be x2 and not x3 and x4 and not x9. So I'm not going to address it now. You can think about it. It's going to be harder. Okay, so protocol 2. There is a teacher who knows the hidden function, and the teacher is going to provide examples. And you, as the student, will learn from these examples. So now pretend that you're the teacher and suggest to me examples so that you can learn with the smallest number of examples possible. What examples would you propose? Yes?
Does he just have everything that is not necessary to be 0 and everything that is necessary to be 1? Would that be giving away the function?
Okay, so the second question that you asked before we address the first comment is a very important question. When we develop these kind of protocols, these are called teaching protocols. I want to make sure that I'm not giving you the function. I want to teach you and I want to force your learning algorithm to do some work. So it's a non-trivial thing to define fair teaching protocols from a theoretical perspective. But let's set this aside, and let's go back to your first suggestion. So I want to convey to you what are the important variables, right? This is my job as a teacher. How do I do it? What would be a good example to give to start toward this direction? For example, I can give you the all one example. 1, 1, 1, 1, 1, 1, 1, 1. Positive example. What have you learned? Right. So really I didn't learn anything. I just learned that some of these are there, but I knew that ahead of time. Right? It gives me no information. I don't know whether X98 is there, X90 is there, and so on. Yes? Yes, I know that it's a monotone conjunction. What is your suggestion then? Right, no. So we're talking about monotone conjunctions. So, but still, and therefore, when I give you all ones, I gave you no information, right? Because you knew that all the 100 variables are a superset of those that are in the conjunction. Yes?
I'm not totally clear on what the exact objective of the teacher is. If, say, the teacher is trying to get the student to understand the function as fast as possible, then I think it would make sense to just give the example that was mentioned before of, the positive. So if that
what do you mean? So I didn't quite understand from that how to do it. So let's be concrete. So what would be this example that will tell me?
So if the only x's that you needed or the only variables that you needed to be on state were like the second, the fifth.
2, 3, 4, 5, and 100. Yes.
2, 3, 4, 5, and 100. Then you have 2, 3, 4, 5, and 100 be 1, and everything else be 0.
Yeah, excellent. So sorry if you said it before and I didn't get it. So here is an example that is proposed. Take the 100 bits that you have, put 0 in all of them except for 2, 3, 4, 5, and 100. These are going to be 1. And ask me this question. What will I say? Let's go back to the hidden function. This is the hidden function here. What will I say if you give me an example that x2, x3, x4, x5, and x100 are 1, and the rest are 0? Positive example, negative example? Positive example. Everyone agrees? What do I learn if you give me this and you tell me that's a positive example? Yeah?
Learning all the other variables that were 0 to 1.
Yeah, that's what I learned. I don't know whether these are important, but I know that all the others are unimportant because it's a conjunction. So I know that those that are on, in my example, are a superset of those that are important. Okay? So that's actually what I'm going to do. So I'm going to give you this example. You can see that 2, 3, 4, 5, and 100 are on, all the rest are off, and it's a positive example. So now I learned a superset of the good variables. How would you continue? Yes?
So then you would just one by one turn all the good variables off to show that each of them is essential.
Yeah. So first of all, you showed me this is a superset of the important ones. And now you're going to turn them off one by one using the same idea from the previous slide and show me that each one of them is important. So for example, you're going to turn off, in this case, I turned off x2. You see 2 turn from 1 to 0. x2 is needed. And the same thing I'm going to do with x3 and so on. How many examples do I need now? 6, right? The 5 important plus the initial superset. So here is a good example. Well, one reason it's a good example is because the teachers are important. Maybe you didn't think about this before. The second is that it shows you the different protocols actually are different, right? So the first protocol, we had to see 100 examples. In this protocol, 6 examples. It's the same hidden function. All we changed is the learning protocol. Yeah.
Wait, why can't we just like keep them all ones and then turn off the ones that are important to show that? So like start out with all the ones and then turn off x2.
Okay, good question. So let's change it a little bit. Start with all ones, all the 100 are 1, and then turn off x2, x3, x4, x5, and the next 100. And this way I show that 2, 3, 4, 5, and 100 are important. What is missing, though? Yeah? Yes. So with this, I still don't know that the other ones are unimportant. And if I show you a negative example with only these, positive example with only these, I know that. So, okay, so I think we learned a lot from these 2 examples. But, and again, I learned the hidden conjunction exactly. The exactly is actually an important word here. And I also already comment on the fact that modeling teaching actually in a clear way is actually tricky. Protocol 3. So in the case of protocol 3, I don't control which examples are going to be observed. And here is what someone gave me. So here is a set of examples with their labels. How do I use it? In general, even before you see the examples, how would you learn a conjunction? So now that we played a little bit with conjunctions, hopefully you have intuitions, yes?
So for each individual variable, you can look at all the places where it's 1, all the places where it's 0, and if, say, it's plus everywhere that variable is 1 and minus everywhere that variable is 0, then you know that that's, or you don't necessarily know, but you can kind of check it off as one of the possible candidates. Whereas if there's a variable where when it's 1, there's some pluses and some minuses, or when it's 0, there's some pluses and minuses, you know that's not one of the variables.
Okay, so let's say again what you said in a maybe slightly simpler way. Suggestion?
Look at the example that has the highest number of zeros and least number of ones that is true. So then you know the most about which one is important.
Then I know that those that are 0 there are not important. So what is the criterion for a variable to be there or to not be there? Yes?
If it at any time disagrees with like how we classify the example, then we know that it doesn't matter.
So if I see a bit that is 0 in a positive example, this guy doesn't matter, right? It's not part of the true conjunction. That's one direction. The second direction actually may not hold, right? So if I see it 1 in a negative example, I don't know, because it could be that it's the fault of someone else, right? But what I definitely know that if I see someone, again, what did I say? 0 in a positive example, this variable is unimportant, right? And so I can do this by looking at all the examples together, as you suggested, or I can look at it in an online way. You know, you give me one example, I start with believing that all of them are there, and as I see more and more examples, I eliminate variables. And this is the way I'm going to present it here. So as an elimination algorithm, I'm starting with all the literals. If I see a 0, a non-active, in a positive example, I know it shouldn't be there, and I'm going to eliminate it. So I start with all ones, and it's a positive example. Then I saw a negative example. Really, basically, what I just said, what you said, is I don't really learn a lot from negative examples, right? I still know that some of these are unimportant, but I don't know exactly who is unimportant. Now, when I see this example, it's a positive example. All those that are 0 in this positive example, I know do not belong. I eliminate them. And I can keep on going this way. So after this example, I know that all the middle is unimportant. So I know that x1, 2, 1, 2, 3, 4, 5, 99, and 100 could be important. So I keep those as my current hypothesis. I see another example, it's negative, I learn nothing. I see another example that is positive, x99, you see, became 0 here. So I eliminate it, and that's what I have now. Now, all the other examples, negative example, I learn nothing. Positive example, I also did not learn anything from it because everything that I had in my current hypothesis was on. So I didn't learn anything from it. And that's where I ended, right? So I ended with this hypothesis. Is this a good hypothesis? Yeah?
I mean, it's as good as you can get to in the data.
So it's not good in the sense that unlike the previous two protocols, it's not, I didn't learn exactly. Well, I tell you this because I showed you the truth, right? In real life, you may not know whether you're good or bad. But what you know here is that it's not perfect because I did not eliminate x1, but you said it well. So given the data that I've seen, it's the best I can do because I've never seen a negative example with x1 on in it. Oh, sorry, a positive example with x1 off in it. And therefore, I never eliminated x1. I still think, given the data I observed, that x1 could be there. What does that mean on the future? So now I take this hypothesis. I believe that that's the truth. I'm going to use it to classify email. What does that mean? Yeah? I don't know if it's bad, but it's going to make mistakes, right? It's going to make mistakes because if I'm going to see x1 off in an example, immediately I'm going to say it's a negative example, but it could still be a positive example because x1 really doesn't belong in the true hypothesis, right? So I will make mistakes. Now, is it really a bad classifier? Okay, so we don't have tools to put a number on it, but what do you think? Yeah?
We update it as we go on. So it's bad at the beginning.
Okay, we can improve, but let's assume we don't, right? So from now on, we never get more labels, we just run. Other people, well, what do you think? Good classifier, bad classifier? So there was a comment that it's the best you can do. Yeah.
I don't think it's necessarily the best we can do because there are things that this approach misses. For example, we learn nothing from negative examples, but it doesn't necessarily have to be that way because what we do know is that if we have a negative example, then some of the ones that are zeros are necessary. And if, say, we have a situation where we've already learned that all except one of those variables that are zero are not necessary, then we can conclude that that one variable that we don't know.
So it's true that we might have, with specific combinations, we might have been able to eliminate x1 even without observing a positive example with x1 on, but this would be a very specific configuration, and it doesn't happen in this data. So with this data, that's the best I can do. So, but you could say something like, well, in the training data, you've never seen any positive example with x1 off, right? Have you? Agree? Disagree? We've never seen, I'm claiming, in the training data any positive example with x1 off, right? Otherwise, I would have eliminated it. So maybe these examples are just, they never happen. So there is some distribution that governs the generation of the data. My training data was sampled from this distribution, and I've never seen an example with this property. Maybe I'll never see. Or maybe it just indicates that the probability of observing these kind of bad examples is very low. So even in life, I will hardly see these. So it's going to be a good classifier, right? So on examples of the type I've seen in the training, it's going to do well. So this is one potential way to think about it. And we will quantify this way of thinking a little bit later. Before that, I want to ask the question of the number of examples. So what is the number of examples that we need here? So we needed 100 in the first case, 6 in this case. In the second case, how many here? Actually, we don't know, right? Because, first of all, we did not converge. And let's assume we converge to this and we are happy with this. Also, we did not quantify it in terms of number of examples. Someone can give us a lot of examples that are identical or very similar, and maybe we didn't learn a thing. The way we presented it is we did an elimination algorithm. When did we eliminate? When did we change the hypothesis? You can think about it in the following way. You can think about it. I started by saying that all the examples are positive. And then when I saw, let's see, go back here. I started with saying that everything is positive. I saw this example. It's a negative example, learn nothing. Then I saw this example. What have I learned here? That's what I learned. I learned that this is those that are on are a superset of this example. So I'm getting closer and closer to the function whenever I see a mistake, an example that disagrees with what I'm currently thinking, right? So you could think about it from the perspective of mistakes that you're making. Every time you make a mistake, you change something. You thought that everyone is on, so you said, well, this must be. If you think that everyone is there, what would you predict on this example? Again, if you think that all the variables, like I started with, start with the set of all literals as candidates, what would you say under this assumption when you observe this example? 1, 1, 1, 1, 1, all zeros, and then 2 ones at the end. What would your prediction be? 0, right? And you would have made a mistake. It's a positive example. You made a mistake, and you eliminate a lot of variables. Let's continue. Now you think that x2, x1, 2, 3, 4, 5, 99, and 100 are there. You learn nothing here because for this example, you would have thought it's 0 anyhow. For this example, what would you predict if this is your current hypothesis? 0. But it's 1. So you made a mistake, and you've learned something. What have you learned? That you need to eliminate 99. So every time you made a mistake, you learned something, you eliminated the cause for the mistake, or at least some of the causes for the mistake. So what we can say is that we know how many mistakes we're going to make, but we don't know how many examples we're going to make. And the number of mistakes, what is the largest number of mistakes you can make here? Suggestion there? One above you actually made a suggestion. Yeah. How many? Almost. Almost 100. Why not exactly 100? Someone else here? Why not exactly 100? How did you get to the 100?
I just thought literally the classifier got every single
the example, nature could have generated such that, first of all, we made a mistake due to 99. And then we made a mistake due to 98. And then we made a mistake due to x97. And nature would be so adversarial that it would force us to make a mistake for each variable we have to eliminate. I was very nice to you here, and in this example, the third from the top, I eliminated many at the same time, right? I gave you a lot of zeros, so you eliminated many at the same time. But nature could be adversarial, and it would force you to get them one by one, but it will not be 100, right? How many? 90? Why 99? But will I eliminate 99? You know the truth, right? What is the truth here? It's 5 variables. So I will eliminate no more than 95. So I will make no more than 95 mistakes. And by the time I made 95 mistakes, I eliminated all by the good ones. Okay? So I don't know how many examples this will take, because maybe I will take 1,000 examples here on which I made no mistakes, and then suddenly make another mistake. So we were forced, due to this learning protocol, to move from how many examples we see to how many mistakes we're going to make. Right? We're just forced to, because we have no control at this point on the number of examples. Now, you want to be able to think a little bit whether these are related, but at least it's something that we quantify it in terms of number of mistakes. Okay, so now that we talked about this, and hopefully you got some intuitions, not only to conjunctions, that's a byproduct, but really to the notion of learning protocols and number of mistakes and number of examples, we can really take 2 directions. One is to continue with the probabilistic intuition that I gave a few minutes ago. The idea that I never saw x1 equals 0 in a positive example during my training. It's really an important thing, right? So you can say it's a very bad classifier, but I could say, I never made a mistake due to x1 in my training. Maybe I'll never see this data, right? So think about it. If you learn from text, most of the text that could be generated is never being generated, right? So maybe some examples are just not supported by the distribution. I'll never see them. I don't care that my current hypothesis would make a mistake on them, because I'll never see them. Same thing with images. Most of the combination of pixels in an image will never be a legitimate image. So I'll never see them. So who cares that my hypothesis doesn't do well on them? Okay? So maybe this is the situation here. x1, 0 in a positive example never occurs. I learned something, and it's going to be good. Or at least with high probability, it's going to be good, because I saw so much training data, and it never happened. So hopefully it will never happen in the future. So we're going to try to analyze this probabilistic intuition. It's something that is called PAC framework. PAC stands for probably approximately correct. So that's one step we have to make from where we are now. And the second one is thinking about mistake-driven learning algorithm or online algorithm, which is the type of algorithm that we just discussed, that is, we reason about the number of mistakes, not the number of examples. And we'll think a little bit about it more, and we'll see that actually these two are related. But we're going to start by talking about algorithms that update the hypothesis only when they make mistakes. Okay, so that's the type of algorithm that we just discussed. And it's going to be a very important class of algorithms. Now, not all online algorithms are mistake-driven. You already know about stochastic gradient descent. It's an online algorithm. It's not mistake-driven. It updates all the time. But we'll see that some versions of it that are also stochastic gradient descent algorithms actually are mistake-driven, so they save you updates. The only update where they make a mistake. Okay, so that's what we're going to do now. We're going to learn a bunch of learning algorithms. Perceptron is the key representative. As I said, it is a gradient descent algorithm, but we're not going to look at it at the beginning, at least this way. We're going to look at it really as a mistake-driven algorithm. This will allow us to talk about a lot of things, like the importance of representation again, complexity of learning, and also to introduce an important idea of kernel-based methods. Okay, so let's start talking about mistake-driven or mistake-bound algorithms. So the first thing is, in the previous algorithm that we talked about, it was clear to us, I think, that at some point this algorithm is going to stop making mistakes. Anyone wants to explain why it was clear? I want someone from this central region to talk to me also. I only get people from the coast. Suggestion. Are you convinced that this algorithm, elimination algorithm we talked about before, will stop making mistakes at some point? When? You won't. Suggestion. Yes? Go ahead. When you reach the truth, no more than 95 mistakes, right? Because whenever you make a mistake, you eliminate someone, and there are only 95 things to eliminate, it's going to stop making mistakes. So is it a general thing that every learning algorithm will stop making mistakes at some point? Yes?
We might not know it's making a mistake though. So like say we narrow train here, we never see positive sample of x to 0. So when x 1 is 0, maybe that comes up a lot in our test data, and we keep making that mistake every time.
Right, but let's assume we are training now, and whenever you predict, someone gives you the truth. So now I know if I made a mistake or not. So under this assumption, and this is going to be my online algorithm, my online protocol. So I get an example, I make a prediction on it, someone gives me the truth. So under this assumption, I know when I made a mistake, and in the algorithm that we just discussed, you convinced us that we're going to stop making mistakes after some time. Is this a general thing? Any learning algorithm is going to stop making mistakes?
I think very abstractly, yes. But if, for example, your learning algorithm is to say writing a statement for every possible combination of pixels, theoretically, yes, you will eventually.
Okay.
Such a big number of mistakes to make that it's not really relevant.
Okay, so one suggestion is yes, but it's uninteresting.
I think you need to have a pretty exhaustive feature space to do that. So if you were missing any features, then you would continue to make mistakes.
Okay, so your intuition on both sides of the aisle here is no. It's good that that's your intuition, because what we're going to show is that for actually quite expressive cases, the answer is yes. So I'm going to start now with a relatively simple case, and probably only next time we're going to move to the more interesting case. So what is the simple case? I'm going to assume this. I have a finite concept class. Disjunctions, conjunctions, What we show here is a finite concept class. I'm going to argue that for this case, the answer is yes. Why? The algorithm is going to be mistake bound. We can always have an algorithm that stops making mistakes at some point. Okay, so again, my goal here, this algorithm that I'm going to give now is a theoretical algorithm. Next week, next time, which is also going to be next week, we're going to give a very practical and important algorithm that has the same properties, and it's really magical. But even with the theoretical algorithm, I think it's good for you to think about it. So I have a finite hypothesis class, finite number of functions that I'm considering as candidates. So does it mean that it's bound to make a bounded number of mistakes? Again, there's 1,000 functions there you can choose from. If your algorithm is such that, think about the elimination algorithm, is such that when it made a mistake, so I used one of these functions, one of these 1,000 candidates, to make predictions. You gave me an example. I made a prediction on it. I made a mistake. This function is no longer truth, right? Now I have only 999 candidates. Right? You see? Independent of features and how I represent features, just because I have a finite number of candidate functions that I could learn, I'm bound to stop making mistakes at some point. So here's the algorithm. I'm going to call it con for consistency. In the ith stage of the algorithm, I'm going to assume that Ci is all the functions that are consistent with everything I've seen so far, with the I-1 examples that I've seen so far. Okay, let's say there are 1,000 there. Now, I'm choosing one of these functions that are still consistent in Ci, and I'm predicting with it on the next example. Either I didn't make a mistake, I'm good, let's continue, or I did make a mistake, in which case I'm eliminating it, and now I have a smaller set of candidates, candidate functions. So I cannot make more than size of concept class minus 1 mistakes. Okay? Everyone agrees? Now that you agree, we have 1 minute to tell me if you have a better algorithm than this to make the same point. Yes?
Don't just eliminate one potential hypothesis, eliminate all the ones that aren't consistent with each example.
Great. So I was going to ask, before you said that, what is the most important computer science idea? Computer science algorithm. If you had to choose the most important algorithm, key idea that you use all the time in computer science. Any candidate, suggestion, something? Almost all of you are computer scientists, right? So give me a suggestion. Doesn't have to be right. I want to see what you think. A name of an algorithm. Refuse. Okay. This side, I haven't heard from this side. Give me a name of an algorithm that you've seen in any class that you think is important. Yes? Binary search. This is what I was looking for. So now, and your algorithm is a binary search. So now, and you take it with you for next time, because you will not hear from us. There are no quizzes this weekend. And think about how you take a version of this algorithm using binary search and get closer to it. So what we're going to do next time is start with this binary search algorithm and then move to show you that even in infinite concept classes, actually you can have algorithms that stop making mistakes at some point, which is cool. So have a good weekend. Hi.
About that nature case, you said
About this.
the nature, the last part.
Yes.
You said if you were asking if the right, if it's the good model, the good number of features that we have. You said you had so many examples, and we came to this and never saw any example of X1.
Yes.
What if you don't see any example that X1 is 0? All you see is X1. Would that still be the same thing? Because then you don't know if X1 is important.
Why do I care? So the issue is that, typically in the world, the number of possible examples is much more larger than what you will see, right? Think about 100 features. It's 2 to the 100 examples. You'll never see 2 to that. If you think about 1 million features, 2 to the million, you'll never see it.
So if you do the million examples, and you don't see X1 even ever being 0, would that mean that X1 is not important? Like if you have such a
It's
long
not important because it never changes.
so then you really can't eliminate from what is because
No. Okay, it depends what your hypothesis is. Conjunction, the other way around, I have to keep it the same. Because if I eliminate it from there, okay, it depends whether it's
I'm saying like
0 to 1.
yeah. Okay, and also the question I have.
But in principle, you're right. I don't need it there. I don't need it there. And it will not be there. So next week, when we learn an algorithm, with this kind of behavior, X1 will not be there. Because I will not represent my conjunction as conjunction starting next week. I'll represent them as linear factors with the weights. So from the quiz and from what we said in class, I can do this. And what I'm going to learn are the weights for this. The weights will tell me is X1 important or not. If I'm going to put 1 weight on X1 or 0.9 weight on X1, it's important. If I put 0 or 0.0001 on X1, it's unimportant.
And also what that party said, based on mathematically, if you have, doesn't matter how many features you have, 1,000 and 100,000, at one point you're going to get to the perfect, you're going to converge to the perfect model. They can get all the right values and get all the wrong values.
Yeah.
Because there's limit and everything. Wouldn't that have the assumption that whatever you're saying can be represented in mathematical form? Isn't that a foundation?
I'm not sure I get your example.
So in this case, let's say you have 100 features. And if you assume 100 features is the right number of features, you don't need any more features. That's the max. And you go one by one, you eliminate, you get to the right value, and you test it this model, and then you have all the cases. So you make sure this is a model.
Yes.
This one gets a lot of truth. How would you know after, let's say, 1 million times, this model would always give you a 1 and not a 0? Because how do you know if the model is, if whatever you're trying to predict is mathematically, only mathematically shown, which is what
So you're saying you learn something when you're planning this. It's doing well on the planning. How do you know that it's going to do well on a new day?
Let's say you have to do it so if you do perfect 3 times, how do you know 1 million and 1? It doesn't need it.
So we will answer this. The way we will answer it is what I call obvious. We assume that there are 2 to the million examples. I never see. There is some distribution over this data. And my value data is a sample according to this distribution. Every time I see training data, it will be different training data, but it's sample from the same distribution. That's very important sample from the same distribution. Again, not the same example, but it's the same distribution. I'm going to prove to you that's going to be okay. Or why is actually the right way to say it. Because I will not prove to you that it's going to be 100%.
But I can't say it if it's not.
Very little can be said if you change the distribution. But this is the space. The only sample from here, the only sample from here. So we're going to get there in about 2 weeks. What's your name?
I got a very quick administrative question.
Yes. So let us go there.
Sure.
live like Scott Murray's bedroom.
like